Welcome to the presentation on experimental study of a novel hydrocyclone apparatus for flow separation in a dynamic flash evaporation setup for desalination and water remediation of purification. I am Ashok Tyagarajan, PhD student in J. Mike Walker Department of Mechanical Engineering at Texas A&M University, College Station. Thermal desalination is one of the oldest and widely used technique for desalination. The pie chart on the right shows that seawater is majorly used as feed water for thermal desalination. Thermal desalination is preferred in applications involving highly saline feed water and where a high quality of distillate is required. However, thermal desalination requires high capital cost and is susceptible to scaling and corrosion. To overcome these disadvantages, we need a low-cost, less complex alternative that has smaller footprint and lower energy requirements. Thus, we propose the use of a novel flash evaporator and hydrocyclone phase separator to eliminate the pitfalls of a conventional thermal desalination plant. The motivation of the study thereby is to reduce the capital expenditures and operating expenditures in thermal desalination using our proposed novel apparatus. For this purpose, air-water mixture was used to emulate the phase separation efficiency anticipated from the proposed flash evaporation and phase separation apparatus. Experimental schematic of the hydrocyclone apparatus is shown here. The apparatus consists of an injector block, a transparent test section, and an exit block. The premixed air-water mixture separates into an air core that is retrieved using a retrieval tube, which is placed at the center of the test section while the water exits the apparatus through the water exit block. For the current setup, two tangential injection ports were used to create the centrifugal flow. Solid model of the test section is shown in this slide. Here is a representative experimental video for 2.5 gallon per minute water and 20 SCFH of air. Equations used for data reduction are listed on the slide. Separation efficiency is defined as the ratio of mass flow rate of air to the combined mass flow rate of air and entrained water retrieved from the steam retrieval tube. Uncertainty was estimated using the equations listed on this slide. The experiments were conducted at 2 gallon per minute, 2.5 gallon per minute, and 3.5 gallon per minute of water flow rates. Air flow rates were varied between 20 SCFH and 100 SCFH. The experiments were conducted with retrieval tube inserted 6 inches into the test section. Moving on to the results section. This graph shows the variation of separation efficiency with air flow rate for 2 gallon per minute water flow rate. As it can be seen from the graph, separation efficiency peaks at 38 SCFH and dips due to seeping water droplets from the exit block and entrained water droplets from the air core. There is an increase in separation efficiency as airflow rate is increased beyond 44 SCFH, but it also corresponds to a non-ideal case of air core traveling all the way to the exit block. Peak separation efficiency is around 90%. This slide shows the variation of separation efficiency with airflow rate for 2.5 gallon per minute of water flow rate. Similar to the 2 gallon per minute case, a peak and dip is seen for the separation efficiency. There is an increase in separation efficiency as the airflow rate is increased beyond 60 SCFH as seen in the previous slide. For 3.5 gallon per minute, the peak and dip in the separation efficiency is less pronounced and hence it is preferred over 2 gallon per minute and 2.5 gallon per minute. Peak separation efficiency of around 98% was attained at 64 SCFH airflow rate. To conclude, the efficiency increases with airflow rate, efficiency peaks are observed due to seeping water droplets from the exit block, and maximum separation efficiency of around 98% was attained. I would like to thank the members of Multiphase Flow and Heat Transfer Lab, federal, academic, and industry collaborators, national labs, and research consortiums for their contribution. Thank you.